Magical Mirages, or The Earth is Flat? Response to Taboo Conspiracy. Recently, Ben published a video cataloging a series of images which he claims are flat Earth proofs. We'll take a look at several of them here. After I'd completed this slideshow and was getting ready to write the script, I saw that Ole D had recorded a response of his own, and it is excellent. Sheepishly, I'm reminded that I'm on the JV team, while folks like Ole have skills far greater than mine. I've linked to his video in the description. Ben's video starts with some high-altitude balloon footage, with the horizon below the center of the frame. It looked a little wonky to me, so I compressed it left to right, and sure enough, it is proof that the Earth is concave. Or it's a fisheye lens. Next, he shows No Donk Records footage from a Blue Origin launch, showing what looks like a flat horizon. But if you have an eye for detail, you'll see the on-screen text at the lower left is distorted, and the footage is letterboxed for some reason. Here's the original video from Blue Origin. The curved horizon is distorted due to a fisheye lens, so No Donk flattened it. That's not exactly proof the horizon is in fact flat. Ole did an excellent analysis of No Donk Records footage, starting with various types of lens distortion and an analysis of where individual pixels will move when distorting or correcting the footage, and even a 3D render of the scene. Link to Ole's video is in the description. Now Ben's video begins in earnest with this image from Fabio Longaron of the Italian mountain Monte Viso, or Monviso. Ben uses GitHub's Earth Curve Calculator and includes an image from the Wikipedia entry. GitHub's calculator does not include atmospheric refraction and assumes that the Earth has no atmosphere. The trouble with mountain images is we can't easily visualize their true height above sea level, only their height compared to nearby saddles to other mountains. Can you tell if we can see most of Monviso in this picture? I located where the photo was taken and put it into Peak Finder and found two peaks both 10 kilometers from the camera, which gives us a yardstick, or a meter stick in this case. Knowing the difference in height allows us to estimate the height above the mountains in this image, and it turns out we can see only 1/3 of it here. Returning to the original photo, and again using Peak Finder, we can do a similar analysis, giving us another meter stick, which is a fraction of Monviso's height, which is 4.4 times greater. Starting with the Peak Finder image, we can use 4.4 multiples of the meter stick to estimate where sea level is on the actual mountain. It's interesting that the Peak Finder image matches what we see in reality, while Monviso should appear much, much taller if the Earth were flat, or as some folks like to say, where level equals horizontal. Let's look at the second image from Ben's video, also taken by Fabio Longaron of Monviso, just like the first image. Again, Ben does an analysis using GitHub's Earth Curve Calculator. A number of years ago, folks in the flat Earth discussion were constantly misusing 8 inches per mile squared as an obstruction formula instead of a curvature estimate. It's nice that almost nobody does that anymore thanks to a variety of online calculators. The GitHub one was one of the first, and it's a very simple obstruction estimator with some assumptions, namely that light travels in straight lines. In other words, it assumes that the Earth has no atmosphere. In reality, refraction does exist, as shown by the sun, which looks circular the rest of the time, but here is looking a bit squashed and raggedy. The Earth does have an atmosphere, and refraction is a thing. More on this later. I wasn't able to find an exact location for where this picture was taken, but we do know it was about 250 meters above sea level. Again, Peak Finder does a decent job with a matching virtual camera elevation. It's not clear how this is supposed to be proof of a flat Earth when it so closely relates to globe geometry using an automated tool like Peak Finder. To simulate the actual height of Monviso as seen on a flat Earth, I flew the virtual camera into the air and it added a bit of blue ocean. It doesn't exactly match the original real-world photo. Why is the majority of the mountain obscured in the picture? Let's take a look at the third photo by Mark Brett of Bar des Écrins, which I'll Americanize to Bar Écrins, in the French Alps, and other mountains on the horizon, taken from Finisterre Peak in the Pyrenees. In making this video, I discovered that there's a range limit to Peak Finder. Plus, I noticed belatedly that the quality is lower than another mountain visualizing tool, Ole D'Haeseleer panoramas. It can also color code based on distance. Here are the mountains shown in Mark's photo. Again, this globe-based tool lines up quite nicely with real-world photography. But what about flat Earth proof? Ben's video is seriously lacking in any sort of analysis with these long-distance mountain images, and what would be expected on a flat Earth. It turns out that only 1/10 of Bar Ekran's was visible in the original photo, while the mountain should be an order of magnitude taller if the Earth were flat and level. A fun thing to do is to compute the angular size of distant objects. In this case, the 4,102 meter tall mountain at a distance of 440 kilometers, resulting in just over half a degree in angular size. The full moon is a bit smaller than that, scaled to the lens the photographer used, lined up with the top of the mountain. And again, we can estimate how tall the mountain would appear if the Earth were flat and level, rather than having most of it hidden by Earth curvature. Our fourth photo is also by Mark Brett, taken across the Gulf of Lion in the northwest reaches of the Mediterranean Sea, of several mountains in the Alps. It was fascinating to me the level of detail that is shown in Ole D'Haeseleer panoramas when compared to real-world photography. Far from being impossible on a globe, they verify globe geometry to a high degree. Color-coded for distance, here's a close-up of the distant mountains shown in the photo, most notably Grand Ferrand in France, at the southwest edge of the Alps. Again, the globe-based geometric simulation matches nearly perfectly with real-world photography. Meanwhile, there's a head-scratcher as to why the 2.7-kilometer tall Grand Ferrand isn't visible at full height if the Earth were flat, simulated here, to scale. Real-world photography matches the globe geometry, while rebuking a flat Earth where level and horizontal are the same thing. We'll conclude with this photo by Wanjo Diaz and Mark Brett, also of Bar Ekran's, a whopping 412 kilometers away from Mount Canigou. To make it easier, I'll color the Gulf of Lion blue. While the mountains look like clouds, an analysis using Ole D'Haeseleer panoramas shows a perfect fit. Amazingly, Ben included a quick glimpse of this image in his video. A quick 1.6 seconds, almost a hint that he knows the truth of our Earth. Yes, I counted. This close-up image shows the amazing range of distances from orange, 170 kilometers away, through purple, 330 kilometers in distance, all the way up to the teal-blue summit of Bar Ekran's, 412 kilometers away. And this computer-generated image, knowing only the exact location of the camera, matches nearly perfectly with the real-world photo. Yet again, only a fraction of the mountain is visible, with the bulk of its height hidden. Here's a visual of what it would look like if the Earth were flat. Let's take a few moments and compare the flat Earth image of Bar Ekran's height compared to what we really saw in the photo. There is no explanation on the flat Earth why so much of a mountain would turn up missing. What Ben focused on in his video was pure globe geometry with no atmospheric refraction. Here's how much of Bar Ekran's would be showing if the globe Earth had no atmosphere and light traveled in perfectly straight lines. But the Earth does have an atmosphere. Flat Earth folks must deny a lot of math, geometry, and physics to maintain their model. In this case, Snell's law of refraction. Basically, light will bend as it passes through a different medium with a different refractive index, such as air and glass. The light can start in air and enter glass, or it can start in glass and enter air. Here's an image showing more of a gradient with a range of media with progressively less densities. If we flip the diagrams so they match, we can summarize them as follows. In a density gradient, denser medium at the bottom, light is bent downward. Distant objects will appear slightly higher than they actually are. This is a bit counterintuitive, So let's illustrate it with a butterfly. If we add an observer and follow her gaze, we can show that she will see the butterfly much higher than it actually is. She sees its apparent location, while the light rays are bent down to intersect the actual butterfly. Shining lasers through density gradients can illustrate this well, as shown here in this demonstration by Laura Waller with sugar water. She used an ingenious method. She made a thick slurry of sugar water, then froze it solid. She then put it at the bottom of a tank of water and allowed it to melt, producing a density gradient. We can estimate the angles of the beams as they enter and exit the tank. Here it turns out that the laser bent about 18 degrees and 18 inches by coincidence. We can make a nice ratio of 1 degree per inch, which isn't technically what's happening along the beam, it's just a ratio, so we can make comparisons. Let's return to the pure geometry of an atmosphere-free globe obscuring almost all of Bar Ekron's. Let's compare it to the real-world photo, watercolored blue for contrast. Remembering that light bends downward in a density gradient, we can ask a simple question. How much will light need to bend downward in the atmosphere to produce this photo, if the Earth were a globe? It's a simple math problem resulting in a ratio of 35 hundred-thousandths of a degree per kilometer, or 1 1/4 arc seconds per kilometer. That's not a lot of bending. So yes, the actual photo shows the common complaint of flat Earth folks. We see too far. Specifically, we see 1,044 meters of Bar Ekron's. That should technically be behind the geometric horizon if there were no refraction. Let's take a look at a better Earth curve calculator, such as the one at Metabunk, and plug in the values for the mountain's distance and viewer height. In his video, Ben correctly pointed out that the geometric value for hidden is 3,920 meters without refraction, which requires the Earth to have no atmosphere. So let's take a look at standard refraction. It shows 2,920 meters hidden, a difference of 1,000 meters. It turns out the photo differs from globe prediction by only 4%. Another way of looking at this is the image of Bar Ekron's shifted the tiny amount of 1500ths of a degree after passing through 412 kilometers of atmosphere. Refraction is a very subtle effect and does not work miracles. Over great distances, however, the differences can add up. Meanwhile, there is no explanation on flat Earth for why so much of the mountain is obscured bottom up. Perspective doesn't cause this effect, nor does the Rayleigh criterion or human eyeballs. I've often found it ironic that flat Earth folks would be so outraged at a claimed tiny fraction of a degree of atmospheric refraction, while ignoring the elephant in the room with their own model, illustrated by Walter Bislin here. Ole D. pointed out that light needs to bend up to 180 degrees to make a flat Earth even imaginable. That is, seeing something in front of you that is actually behind you. Here's an example of what Ole is talking about. When the Southern Cross is high in the sky at Cordoba, Argentina, it's near the horizon for Perth, 180 degrees of longitude away. Yet, in the flat Earth model, the southern celestial pole does not exist, because all heavenly bodies exist in a dome-like firmament. Let's say folks look south from Perth. Their gaze will reveal an inverted Southern Cross just above the horizon, while folks in Cordoba see it high in their southern sky. People in Perth are looking south to see something behind them, with no apparent distortion, amazingly enough. A further irony is that Walter Bislin created the flat Earth dome model to highlight the ridiculousness required in trying to make sense of real-world observations with a flat and level model of Earth. Flat Earth folks then adopted this as their own, renaming it the Personal Atmospheric Dome or the Azimuthal Grid of Vision. The experiment truly escaped the lab. A key flaw in the flat Earth model is highlighted here. Light must bend differently for different observers depending on latitude. There is no known physics that explains how this could happen. Remember, the photos of mountains in Ben's video were claimed to be impossible on a globe because they required 1,500ths of a degree of refraction. Yet nothing in the flat Earth firmament or dome exists where it appears. Seeing the Southern Cross right on the horizon from Perth requires not 0.15 degrees, not 1.5 degrees, not 15 degrees, but about 150 degrees of image displacement. That's 3 orders of magnitude greater than what is supposed to be impossible on a globe. It does remind me of Matthew chapter 7, verse 5. Thou hypocrite, first cast out the beam out of thine own eye, then shalt thou see clearly to cast out the mote out of thy brother's eye. It's easy to cheer on one's own side while jeering your opponent, but I'm a teacher, and I only take sides with the truth. I wish that everyone, my students as well as my flat earth friends, and even my Glober compatriots, would hone their critical thinking skills. Critical can often mean important, such as critical medical care. But I believe critical more vitally shares a root with criticism. Look at things with a skeptical eye. Don't just swallow what the echo chamber feeds you. Actively seek out people who disagree with you, not just to argue, but to learn and understand. As Stephen Covey wrote, seek first to understand, then to be understood. That about wraps it up. Thanks to my channel supporters, Johnny Ragadoo and Luke Filewalker. Rest in peace, Jim Jackson. And to my patient audience, thank you so much for your time. And as always, please leave a like and share. And your comments are welcome. Please be kind to each other. Bye.